So we're just going to look at some equations and some stuff similar to what your homework is in class today. And so here's a problem, and we've been doing implicit differentiation, just to remind you, and working with a chain rule. So here's a problem that says find the lines that are tangent and normal to the curve at the given point. And we're given that our equation is y equals 6 sine of, and this is our argument of sine, pi x plus y. And then we are looking at that tangent line and that normal line at the point -1, 0. Okay. So two things we need when we're finding the equation of line. So let's just think about our tangent line. We need a point and we need a slope. And it's to this curve, the tangent line is on this curve. And so we can find the slope at this point. And so let's first, and we want to find that slope at that point, we need to find the derivative. And so we want to take the derivative of this. When we take the derivative of this, we have to be careful because notice that this has both x and y on that one side of the equation. And it would be hard to get y by itself. So we're going to use implicit differentiation. And y, recall, is a function of x. If it helps you, I think it's really helpful actually when you first do these. Y is just the same thing as f of x, is to write these with that f of x in there. Just to nail down that point, this is a function. And when we take the derivative, we're going to need to think about using the chain rule. So I'm going to just rewrite my problem as f of x equals 6 sine of pi x plus f of x. So let's go through and take the derivative. And so when we take the derivative of f of x, let's just write this as f prime of x. This is equal to, so here I notice we're going to need to use the chain rule. So our outer function in this case is sine. And so we have this 6 out here. That's not going to affect anything. And so taking the derivative of sine was cosine. Chain rule, you take that of the inner function, which we will rewrite as pi x plus f of x, times that derivative of the inside. And so if we take the derivative of this inside with respect to x, well, the derivative of pi times x, pi is just a number, that's just going to give me pi, plus the derivative of f of x. So let's just write that as f prime of x. Okay, so notice that we can actually distribute. We can distribute this whole grouping right here in to wherever we see or each term in that other parentheses. So I'm just going to rewrite this. So f prime of x is equal to, so distributing this, I'm just going to put the pi after my 6. So I would have 6 pi cosine of pi x plus f of x. And actually, while we do that, if you don't mind, that's okay. Actually, if you don't mind, let's rewrite f of x as y, right? Because f of x is y now. And then we're distributing it. So plus, so that whole grouping times the derivative f prime of x. So I'm just going to put that f prime of x out front. So f prime of x all times 6 cosine pi x plus, we can just write that as y, f of x as y again. So I just distributed that grouping to each side. So notice that there's two places where we have the derivative function f prime of x, and that's what we're trying to solve for. Because that would find, then we can find what the slope is. And so the trick is to get everything with that term that we're trying to solve for, or variable, or in this case, a function f prime of x, to one side of the equation, and we can factor it out. So if it's okay, as I move this one to the other side, I'm going to actually just pull it out. So if I pull f prime of x out of this first term, f prime of x on that left-hand side, that would just give me a 1. I'm moving this to the other side, so I'm subtracting it, minus, I pulled the f prime of x out of that piece, and so now we're just left with 6 cosine of pi x plus y equals, and so we just left the term without the f prime of x on the one side, so 6 pi cosine of pi x plus y. So almost there where we have the derivative, we want to divide both sides by what I have in brackets there to get f prime of x by itself. So we can see that the derivative of f of x is equal to 6 pi cosine of pi x plus y all over 1 minus 6 cosine of pi x plus y. So we actually want to evaluate this, and we're given our point. We have a point at the slope we wanted at when x is -1 and y is 0. And so we're going to evaluate this. And I'm just curious, because that notation to me, and I was thinking about this the other night, if that should be like, because we have x and y in there, notice we've always been doing this dy dx instead, and then evaluating it here at -1, 0. There's sometimes when you write functions and you have more than one variable and you kind of write it like this, but I don't think so. I don't know. I'm going to ask about that. Anyways, so let's plug in -1 wherever we see an x and 0 wherever we see a y. So actually, I'm going to just write it as dy dx because I know how to do that notation. -1, 0. So 6 pi cosine pi times x, which is -1. So that's going to give me negative pi plus y, which is 0. So I don't have to add that. All over 1 minus cosine. Again, if I plug in -1 and 0 to that pi x plus y, we found that that was negative pi. This is actually where some trigonometry is helpful. Well, I guess we don't have to.
Wasn't it 6 cosine in the denominator?
Thank you, thank you, thank you. Dropped off my 6. We don't have to do this, but this is where, if you remembered that cosine was an even function, that f of -x is equal to f of x, we could rewrite that cosine of negative pi as the same thing as cosine of pi. Or if you want to think about it with a unit circle, if we do negative pi, that was just telling me we were going clockwise versus counterclockwise. Negative pi would get me to the negative x-axis. Cosine is our x value of that point on the unit circle, and so that would be -1. And so we can simplify this. So this is equal to 6 pi times -1, or -6 pi, all over, I'm sorry, not, why did I, yeah, because of the pi here. Just want to make sure I didn't drop off any other pi. I didn't. Okay, so 1 minus, So again, cosine of negative pi is -1. So this is -6 times -1. So this is going to be +6. So this is equal to -6 pi sevenths. And so this is the slope of our tangent line. We wanted to find the equation of that tangent line. So we need two things when we're finding the equation. We need a point and we need the slope. And so we have two things. We have this point, -1, 0, and this tangent line. I'm sorry, and the slope of the tangent line. So we've been using the fact y equals mx plus b, plugging in what we have for y, our slope, our x of the point, and figuring out what b is. So our y value in here is 0, equals our slope, which is -6 pi sevenths. All times x, which is -1 plus b. So -6 pi sevenths times -1, that's 6 pi sevenths, right? Negative times negative is positive. And so then we would have to subtract -6 pi sevenths to get b by itself. So our equation of the tangent line this is our slope, -6 pi sevenths times x plus b, which is -6 pi sevenths. I don't like that box. Okay. So let's look at that, and then we're going to get the satisfaction of getting the positive feedback from my math lab. And then we'll do the second part of the question, which asked us to find the normal line of the curve of that y equals sine of pi x plus y at that point, -1, 0. Okay, so we got that satisfaction of the good job. And so now we're going to look at part 2, and part 2 asked us to find the equation of the normal line. And that normal line, that is basically, the normal line is perpendicular to the tangent line at that point. And so you have to go back and think about what it means to be perpendicular. And so for this tangent of our norm, I'm just going to put norm here for normal line. This is equal to the perpendicular of our other slope. Our other slope was -6 pi sevenths. And so if you remember, and I put 6 there for some reason, but I said 7. If you remember, your perpendicular slope is a negative reciprocal. And so opposite sign, so this is going to be positive, and this is going to be 7 all over 6 pi. So we have, again, a point. We have a point on the line, which was, that had a negative here, -1, 0. So again, we can plug in our values for y, m, and x to solve for b. So we have 0 is equal to our slope, 7 over 6 pi, not 7 pi, times -1 plus b. So let's add 7 over 6 pi to both sides. So we get b is equal to 7 over 6 pi. So we know the slope of the normal line and the y-intercept. So we have the equation y is equal to 7 over 6 pi x plus 7 over 6 pi. Maybe plug in their norm. Okay, so my guess is we got this one right too. But we got to go back anyways to get another problem. So let's just do that. So this one was 7 divided by 6 pi. Come out and it was positive, right? Plus 7 over 6 pi. Uh-oh.
You forgot an X.
Oh, thank you. Yeah, some like silly things like that. And we are excellent. Okay, so we're gonna find another problem and then we'll come back to the recording. So our next problem, it says the graph of y squared equals x cubed is called the semi-cubal parabola. Determine the constant b so that y equals negative 1/3 x plus b meets this graph orthogonally. Okay. Okay, so I just needed to think a little bit about it. So determine b so that y equals negative 1/3 x meets this graph orthogonally. So let's think about it first. If it was not, it was a tangent line. What would the slope of that tangent line be? If we know that the orthogonal line was this. So we know that the slope of the orthogonal line is negative 1/3. We know the slope of the tangent line is 3, right? Because it's perpendicular. So we know that the slope of the tangent line is just 3. Well, we know how to find a slope of a line or a curve. And we want to find that slope of the curve, that point, or that x or y value, right, when our slope is 3. So first thing that we need to do is we need to go in and we need to find the derivative of our function y squared equals x cubed. So let's do that. And so taking the derivative of y squared again is f of x. So we can think of that as we have to use the power rule. So again, if it helps you, and I think that it might just be good just to do this when you first are doing this, learning implicit differentiation. So if we took the derivative of the left-hand side, we're going to use the chain rule, the general power rule of the chain rule, where we bring our power down front. And that is going to give us 2 of the n side, which is just f of x. Subtract 1 from our exponent, so we just have 1 times the derivative of the inside, which is f prime of x. This is equal to, so taking the derivative of the right-hand side, derivative of x cubed is 3x squared. So when we get this derivative by itself, so we can divide both sides by 2f of x, which is the same thing as 2y. We can write that. So f prime of x is equal to 3x squared all over 2f of x, or 2y. So we are trying to find when is this slope equal to 3. So if we know our tangent line is equal to 3 there, then we know that the equation of the normal line going through that point is the reciprocal, negative reciprocal, because it's perpendicular. And so we can set this 3x squared 2y equal to 3.
How did we get the 3 for the tangent slope?
Good question. So we got the 3 for the tangent slope because it says it wants me to determine the constant b so that this y equals negative 1/3 x meets this graph orthogonally. And so I need to figure out if it's meeting it orthogonally at some point. So we're trying to find this point right here. Let's see about this. I'm gonna have to think about this a little more, but I think we're going in the right direction. Sometimes with mathematics, you don't know, you're just you're thinking about it and working it and hoping that what you're thinking is correctly. But I do know this part because it's told me that this line is orthogonal. I know that slope is this right here. So this is my slope of my normal line is equal to negative 1/3. And I know that the slope of my tangent line, which the derivative gives me, the slope of a tangent line at any particular point on the curve, is the perpendicular to this slope. And perpendicular slopes are negative reciprocal. So opposite
So
sign and flip it.
it was just working backwards from that. I see.
Yeah, exactly. And so now we found the derivative, so we can find the slope at any particular point that falls on that line. And we're setting this equal to 3 because that gives us the slope of the curve. Okay, so really technically what we're trying to find right now too is what is this point? Because if we know this point, and we know that our slope is negative 1/3, we could figure out what b has to be. And so let's solve for y here. So let's clear our fractions and multiply both sides by 2y. And so if we do that, we get 3x squared is equal to 2y times 3, which is 6y. Divide both sides by 6. We get that y is equal to, well, 3 divided by 6, that's going to leave me with a 1/2 x squared. So just divided both sides by 6. So what is this telling us? Anyone know? This is equation. This really isn't a point.
So can we just like put in, sorry.
No, go for it.
So can we just put in like any point, like if we put like x is equal to 1, then what's y, so that we can find an ordered paired, and then we can just.
So that this is telling me that, right? And were you going to say the same thing, Noah?
I actually had a different thought, but
Okay.
I was wondering, is the derivative of, or is dy dx, or I guess the f prime of x, wouldn't that be equal just to the equation of y? And then we've got the tangent slope, and then with that we find b, but I was wrong because then we wouldn't have x. So yeah, that was my thinking.
I wasn't following all of that train of thought that you had, but and I apologize sometimes. But what Gurjot was saying, I think is correct, that this is telling us that our slope, we're going to have a slope of our tangent line 3 at many different points on this graph. Would it be?
I was thinking maybe a system of equations.
Okay, so why a system of equations? And you might be totally right. Was there any reason why a system of equation?
Not really.
Okay.
Kind of popped into my head.
Okay, no. So let's look at this. And then the other thing is, does this make sense? So I'm just gonna pause as I think.
I also saw.
Okay, so I decided to turn on the video as we had discussion, just because I think that it's great discussion, and one of you verified that it might be beneficial to somebody who's watching this video to get some help, or a student that missed class. So we have this y squared equals x cubed, and so Ella had mentioned that maybe we should, or how she approached this problem was that she first solved for y instead of having y squared equals x cubed, taking the square of root of both sides and having that plus or minus. And then she talked about then maybe just looking at the first quadrant, because you can see that this is here. The thing is that notice that if we were in the second quadrant, look at this line. Or not line, but look at that curve. Is that curve positive or negative? Is that increasing or decreasing at this portion of the graph if we're looking below the x-axis? Well, it's decreasing below the x-axis, and so we would know that that slope is negative. So we would not get one of those lines anyways, or a tangent line that was positive below the x-axis. Okay, so the thing is, if I know if I put 0 in there, I get 0. But does that mean that my slope here is 0? Is my reasoning right now? I know that if I put in 2 in here, you know, I'm going to get a different value.
So what do we put x equals 4 then? 4 cubed is 64 and square root of 64 is 8.
You don't have a square root in that function. Like in this, I would keep it at this function. Oh. Okay, so just because class is almost over and I want to talk to students and we kind of worked this out. So we did rewrite our original equation, y squared equals x cubed. If you take the square root of both sides, same thing as a 1/2 power of both sides, that gives us y is equal to x to the 3/2. Square root, we would put the plus or minus, and we'll talk about that later. We are in the first quadrant, and -4, our answer wouldn't have worked out. So anyways, we took the derivative, bringing down our power 3/2, subtract 1 from our power from 3/2, so you got 1/2. And then we rewrote the square root, x to 1/2 as the square root of x. And then once we did that, we then set the derivative equal to 3, like we were talking about before. And then solve for x, we got to get rid of 3/2, multiply both sides by 2/3, the 3 cancels, and we're just left with 2 equals the square root of x, and x equals 4. That gives me my x value on this curve. And I need to figure out like this too, but I'm only looking at the one above. I need to plug this into my original equation to find out what that point is on that curve. And so if I do that, remember my original equation was y squared equals x cubed. And so if we plug in 4, we get y squared equals 4 cubed. 4 times 4 is 16, 16 times 4 is 64. So we get y squared is equal to 64, and y is equal to plus or minus the square root of 64, which is 8. And so we have our point now is 4 and we were above the x-axis on that curve. And so we have our point. We have our slope, told us that at the original, it was -1/3, and we need to figure out what b is. And so if we plug these values back into y = mx plus b, we can figure out b. So we get 8, our y value equals our slope -1/3 times x, which is 4, plus b. So 8 is equal to -4/3 plus b. So I'm going to add 4/3 to both sides. And I need a common denominator to add it to 8. So multiplying both by 3. So, I'm sorry, multiply 8 by 3. So that gives me 24/3 plus a 4/3 equals b. So b is 28/3.
I have a question.
Yep.
So for the slope that we decided to use, why didn't we use 3?
We did use 3.
Oh,
Oh, wait. Oh, that was to help. The reason why we used 3 was because we were looking at the equation of the tangent line.
mhm.
The equation of the normal line, we needed the tangent line. We needed to find this point here because the derivative tells us the slope of the tangent line. But we know that the normal line is perpendicular. And so we just use that fact to get this point right in here.
Okay.
And
I see.
that, then we were going back to this equation, which is really small now. We're trying to figure out b of this equation when x is -1/3. So our x value, we want to find that b value.
Awesome. I think I was accidentally looking for the b of the normal line.
So this is the normal line. So if you kept it as 3, you would have been looking at the equation of the tangent line, the b value where that would have crossed.
In that case, I mixed up which slope was which. Awesome. Thank you.
And so we're there basically. Well, they just wanted our b value. If we wanted to list out the equation, we could do that too. It would be y is equal to that -1/3 x plus our b value of 28/3. Pause. So we have find dy dx. We're given e to the 2x equals sine of x plus 8y. Notice that we have y and x on the right hand side, and we could probably solve for y, but that might not be very fun. We'd have to take the inverse sine, etc. We don't even know how to take the derivative of an inverse sine yet. Coming up soon. Anyways, so let's find this derivative. Notice when we take the derivative of e, this has the 2x power, and so we have to use the chain rule. The derivative of e raised to some power other than x, or even x itself, is the derivative of the exponent. So the derivative of our exponent is 2x times the original e to the 2x, equals. So again, I have to use the chain rule here. My outer function is sine.
Wait, wouldn't it be 2e to the 2x?
Yes, you're right. I don't know why I put x. Derivative of 2x is 2. So derivative of sine, we know, is cosine of our inner function, which is this x plus 8y, times the derivative of our inner function. So the derivative of our inner function, derivative of x is 1, plus the derivative of 8y. And so y is in terms of x, that function f of x. So taking the derivative of that, that's going to give us 8 times the derivative of the inside. So dy dx. Okay, so our goal is to get dy dx by itself. And so even though it's ugly, or it can still distribute, And so then we would just have one grouping with dy dx and we can get that by itself. I guess we could also divide by this cosine of x plus 8y2 and then subtract 1, and then divide by 8. But I think it's easier and nicer and cleaner if we first distribute. So doing that, we have 2e to the 2x equals, distributing this, well, cosine of x plus 8y times 1 is just cosine of x plus 8y, plus this times 8 dy dx. So 8 cosine of x plus 8y, all times dy dx. And dy dx is what we're trying to get by itself. And so we want to get all the terms that are groupings that don't have dy dx on one side. And doing that, we're going to get 2e to the 2x. Let's subtract cosine of x plus 8y equals 8 cosine of x plus 8y, all times this dy dx. We want to divide both sides by that. And so dividing both sides by what's in front of our dy dx, we get dy dx by itself. And this would equal 2e to the 2x minus cosine of x plus 8y, all divided by our 8 cosine of x plus 8y. There's nothing I see that I can factor out in the numerator that would cancel with anything in the denominator. I could technically rewrite that as 2 separate fractions and then simplify, but I don't think that is making it any simpler. Okay, so implicit differentiation of x minus cotangent of x times y equals -6, and we want to find dy dx using implicit differentiation, which I just said. So looking at the derivative of x, that doesn't have a y in it, so the derivative of x is just 1, minus the derivative of cotangent. It has the co in it, so that tells me that the derivative is going to be negative. And derivative of cotangent is the cosecant squared of the inside xy. So that was just the outer function. I have this inner function, so I need to multiply by the derivative of the inner function. But notice that this inner function, when I take the derivative of this, I'm going to need to use the product rule. So when I take the derivative of the first piece, x, that gives me just y, plus the first, which is x, times the derivative of y. So I'm taking the derivative with respect to y, that's 1, but it's is a function in terms of x. So I'm going to write down dy dx. And this is all equal to, so that was just the left-hand side of our equation, the derivative of -6, and the derivative of a constant is 0. So let's rewrite minus a negative as a plus. And let's subtract 1 on the other side. I'm going to kind of do a couple things at the same time. And we're going to distribute positive cosecant squared x times y, all times our y, and all times our x times dy dx. So if we do that, I'm going to put the y out front. We would have y cosecant squared of xy plus, I have this x, y, oops, no y, x, dy dx. I distribute this, so it's cosecant squared xy. And we had subtracted this one on both sides. So our goal is to get this dy dx by itself. So we want to isolate that term with dy dx on that side of the equation. And then we can divide through by what that is multiplied to the dy dx. And so I'm going to subtract that y cosecant squared xy to both sides. And we would have x dy dx cosecant squared xy equals -1 minus y cosecant squared of xy. And now let's divide everything through by this x cosecant squared of xy. And that would give us what dy dx is. So dy dx equals, part of me wants to pull out a -1 on top, but it should give us the same thing. But -1 minus y cosecant squared xy all over x cosecant squared of xy.